Now, the point is that, oh, what is this? Maybe I can erase it. Yes, thank you. So actually, you may study this, but because what we set in this paper as possible is actually natural in this type of picture. So actually, even now, this type of approach seems to be the most attractive ones for me. I should do, sorry, and then do, doesn't work. Sorry. Yeah. Yes, yes. So I will start from here, okay? And then after that, what we should do is to first determine the mass hierarchy, because without knowing the mass ordering of 1, 2, 3 neutrinos, it's very, very difficult to start thinking. So this is really important. And in order to do this, there are essentially two ways. And one way is to make use of the matter effect, just like in solar neutrino oscillations. Okay, but in order for the matter effects to be competitive with oscillation with a large mass square difference, we need to have a rather long distance. And this is the idea which I pursued by introducing idea that if we have a second detector in Korea along the T2K baseline, we have two different traveling distance. And if we tune the Korean detector location such that the energy is larger, then actually we can observe similar L over E. L over E is essentially the phase of the oscillation. And if there is a difference between different distance for the same oscillation phase, it means that this difference is solely coming from matter effects, because the matter effects grow with length, right? So that's what we studied. And then I also studied the possibility of using atmospheric neutrinos with the Pingu detector proposal, which existed in those days for putting a very, very fine detector in the core of an ice cube detector. That's very nice. Okay? But it didn't work out. So neither of these worked out. So those works were just theoretical studies. And then there's a completely different idea that we don't need matter effects, because oscillation phase of M3 square minus M1 square and M2 square and M1 square interferes in the opposite way if we see small oscillations around the big oscillations. This is the one which survived and now being pursued by Juno experiments. Let me explain a little bit. So this is the Korean idea, and which I really like. So this is J Park, and Kamioka is here. And Kamioka is about 2.5 degree upside of this neutrino beam. And the neutrino beam center appears on the Earth slightly east of Korean coast. So if we choose the detector very near to the Korean coast, then we can have smaller off-axis angle. And although I didn't explain the physics behind, but the important thing about the solar off-axis angle neutrino spectrum is here. So at 2.5 degree for P2K, the peak is around 0.7 or 0.65 GeV. Okay, by making the angle smaller and smaller, higher energy increases, like broadband, but the lower energy kind of disappears, and making the peak of the neutrino energy bigger. So this tells that in the long distance, if we choose the smaller angle, then actually we can view the same. So this peak moves to here. So by choosing a higher energy with a longer distance with the same L over E, we can study the same place again. And then the difference is really matter effects, and we can distinguish mass hierarchy very clearly. And at the same time, this is the difference between nu mu oscillation and nu bar oscillation. At the same time, we can measure CP violation. Okay, possible. And so I'll just go through very quickly that this is my first kind of idea how this may work out. And so the important thing is off-axis angles. So off-axis angles are here, written here. And then the matter, in order to study the matter effects, we should study the matter density inside of Earth. And many, many years later, maybe several years ago, there was a time that this was considered very seriously in Korea. And I thought that this H location, Mount Bissell, sounds very good because at Mount Bissell, the neutrino spectrum is relatively hard. So something around here. So it's, we have the original T2KK idea may work. And then the mass, this is completely theoretical calculations, and it can go very down. So maybe the matter density can go high because of this. So actually it touches this mantle. And because of this, Naotoshi Okamura really studied carefully the map of this along the baseline. And actually, the reason why this map can help us understand the what is happening below is essentially, our crust, where we are standing is like ice on the sea. Okay, our crust on mantle is like ice on the sea, on the water. Okay, if the top of the ice is very low, it means that the ice is very thin. Whereas if the iceberg is very tall, it means that it's very deep. Okay, it's exactly the same. So in this way, we can calculate it, and by using the side band range information, Naotoshi Okamura found this as a matter density distribution along the baseline from J Park to Mount Bissell, and this is the results. And it's very interesting. So actually, none of them are published because these projects were not really started. And but because we got a request, we studied the sensitivity of this possibility that second hyperkamiokande may be placed in this place. What can we learn? And this is, I think it was 1 year. Sorry, I cannot see. Yes, I think it is 1 year. So after 1 year of joint operations, actually the mass hierarchy can be determined with 3 sigma. It means that after 10 years, it can become 10 sigma or something. Okay. And then this is the actually for CP delta measurement, more statistics needed. But the important thing is this is after 10 years. But if we think about the 1 sigma error of the delta measurement, it's quite accurate, no matter where it is. And also, if you're talking about 5 sigma evidence of CD variation or something, then of course it tells that you can easily move this around, and it's quite a big region can be covered. Okay. So this has the idea has had a very great physics reach. Oh, and this is what Juno is doing, but this paper I wrote before anything, even Juno was proposed. So the basic idea of Juno is essentially given here. We study the anti-electron neutrino spectrum between 2 GeV and high energies very, very accurately. Okay, and if the energy measurement is exact, we should observe like this. And the red curve is normal hierarchy, and the blue curve is inverted hierarchy. And you can see that there is a point at which the two oscillation phase agrees, and so there is no difference. And above this red point, the phase becomes so it's kind of opposite. Okay? So you may think that this should be easy, but then the reason why this experiment is extremely challenging is this. At 50 kilometers, if the energy resolution is perfect, then we can see the difference very, very clearly. Okay? We introduce, I'm not very sure if this is realistic now, but I chose the most advanced possible resolution of the detector, their scintillation detector. Okay, and then they say that 6% of oscillator energy is the energy resolution. We impose this into this curve, then all the difference here disappear. Only this piece survives. Okay, so it's challenging. You know, this energy resolution. If you know our Juno colleagues achieve, then they will see it. Okay, otherwise, very hard. Okay, so this is the end of my phenomenology because I did it only in those days. So let me see, 15. Maybe I have still 5 to 10 minutes. Okay.
You started a little bit late.
Yeah.
Several minutes.
Okay. The rest is completely theory, so I can go very quickly. Okay. And when I give, you know, actually, this is so fundamental. So my lecture should change, right? After 1998, I had thought, and this is what I thought. Okay. So first, we can give neutrino masses just by adding right-hand neutrinos, because all the other fermion Yukawa couplings are, you know, doublet and a singlet mixture, right? And because Higgs boson is doublet, we need a singlet. Okay, and this is what I did. Yeah, we did, and this Yukawa coupling looked exactly the same as previously. So in some sense, it's appealing. But the important thing is that Yukawa coupling is extremely small compared to the electron Yukawa coupling. And also, this new hour is really weird because it has absolutely no gauge interaction. Only interaction it has is the Yukawa interaction, which is extremely tiny. Okay, so but this is definitely one possibility for students. Okay, but when we teach students, I don't want to teach something really completely unrealistic. I feel that this is unrealistic. I cannot imagine that this can happen. So the second thing I did, and actually this is my standard lecture in my first year graduate students lecture. Okay? And this is just to introduce. We don't introduce right-hand neutrinos. Okay, we just introduce a higher dimension operator within our framework. Okay? It's very easy, and we can just make a dimension 5 operator, and then the neutrino mass is essentially this new type of Yukawa times vacuum expectation value squared, because there are two Higgs boson. And because it's a dimension 5, the operator is suppressed by some high scale. So if this high scale is very large, okay, like that scale, then it's very natural that neutrino is very light. So at least this is has an explanation why neutrino is so light. Okay, so this is far more realistic to me. Okay, as a theorist. Okay, so this is how I teach in my class. Okay, and in any case, this is the second one, and the final one is oh, this neutrino has absolutely no interactions. But somehow, by setting this right-hand neutrino mass to 0, we impose a very strong constraint that lepton number is conserved. Now, for this lepton number conservation, it's something which we observe in our reality, but we do not have any theoretical basis for lepton number violation. So, because this has absolutely no interactions, no gauge interaction, gauge symmetry suppress this right-hand neutrino lepton number violation. We just introduced lepton number violation. Okay, so this is the large Majorana mass to the right-hand neutrino. Okay, and because there is no symmetry, standard model symmetry which forbids it, this scale can be as large as the scale of the physics. Okay, can be gut scale, and then immediately starting from here, we obtain essentially this operator where this large mass scale is just this Majorana mass. Okay, this is the original seesaw mechanism proposed by Yanagida and others. Okay, and let me see. So sometimes I also teach this, but in the elementary level, I only teach dimension 5 operators. And this idea fits to ground unification, which I really like because it is really the solution of the quantization of the hypercharge program of all quarks and leptons. Okay? And I talked about SU5, but SU5 is inside of SO10. And if SO10 exists, and SO10 breaks down to SU5 at some high scale, then this mass is of the order of this breaking scale. Okay, so it's very interesting. And also inside of SO10, actually we can tell that there should be right-hand neutrinos. Okay, in order for SO10 to be consistent gauge theory. And because we already know that there are 15 quarks and leptons, by adding this, it is now possible that these 16 elements can make a single SO10 multiplet, which is called a spinor representational SO10, which also looks very nice. Okay? But we observe only these because SO10 is broken down to SU5, and the structure of 10 and 5 star survive and perhaps show themselves as a large mixing in lepton mixing sector. Okay, that's just an idea, but this kind of picture is very beautiful. Okay, so that's why I feel that this is a very nice way of going. Oh, and if you are not very sure about the Dirac neutrino mass and Majorana neutrino mass, this is what I teach in my lectures for first-year graduate students. So it's very, very simple Lorentz transformation of spinors. Okay, and the important thing is that we have two types of spinors. One is left-handed, one is right-handed. They have different Lorentz transformation properties. Their difference is only in rapidity, boost. Okay, boost property is kind of opposite between left-handed and right-handed. How do you call it? Lorentz transformation has 3 rotations and 3 boosts. 3 rotations are identical, but boost is opposite. So it's very easy to memorize this. In case of left-handed spinor, it should be if rapidity is positive, the magnitude decreases. If the rapidity for right-handed one, it's kind of opposite. Okay? And probably you know this from the property of Dirac's, wave functions for left-handed and right-handed components projected by 1 plus minus gamma 5/2. So in any case, by knowing this, by doing this exercise, you immediately notice that this dot product, which is can be written like this, also Lorentz invariant. Oh, sorry. The very first thing you immediately notice that because of this, SL dagger SR and SR dagger SR. Oh, sorry, this is SL. I'm sorry, is 1. Okay, and because of this, Dirac mass is Lorentz invariant. Right? And exactly the same way by introducing the charge conjugation operator, we immediately see that by charge conjugation of right-handed spinel transformed as left-handed spinel, and charge conjugation of left-handed spinel transforms to right-handed spinel. And because of this, those are invariant. And then actually for students, this is the hardest homework, but SL sigma mu, sigma mu is a chiral sigma matrix, and this transforms as a Lorentz vector. This also transforms as Lorentz vector. Because of this, this transforms as Lorentz vector. This was done by Dirac, but actually when I was a student, I couldn't really follow all for what Dirac did. But now I can do this on Blackboard because it's only 2 by 2. Okay. So in some sense, if you haven't done this way, please, it's worth doing. Okay. This is cosmological connection, which is very important. And one thing theorists should know is that it's essentially the same physics between QCD and electric theory, because it's essentially SO3 or SU2 components of non-abelian gauge group, which are playing the role. In case of QCD, because the gluons are massless and it's kind of confined, the appearance of the effect is quite different from the electric theory. But what happened is that because of this anomaly piece, the volume integral, surface integral over the whole universe gives a wrapping number called the integer index. But if this index is a given number, there is not much problem, but there is a solution called the instanton solution in massless QCD, which changes this wrapping number. And then the ground state becomes some kind of theta vacuum which violates CP and plot parity. Okay? And in order to avoid this, we may need action. Okay? In case of electric theory, the corresponding wrapping number becomes B plus L. And although B plus L breaking is not so serious at low energies, but we know that the universe was very hot and there was electric phase transitions. And probably there were times when the temperature was higher than the electric scale. And then there's again transition between different B plus L. So actually B plus L is not at all a good quantum number. And because of this, in old days, people thought that in grand unification theory, like SU5 theory, we can have baryon number asymmetry at high energies, which we are observing now. Okay? But all those baryon number asymmetry washes out because of this B plus L washing process. Only if we may create B minus L asymmetry, it can be preserved. Okay? Now, the large Majorana neutrino mass, which we introduced, is lepton number violation, lepton number difference, but it does not have baryon. So B minus L is produced by large Majorana mass neutrinos. Okay? Now, starting from there, after the electric phase transitions, this B plus L part washes out, and after doing this chemical equilibrium calculation, we find that the baryon number is observed now. Okay. This is leptogenesis. Okay. Because of this, it is a very, leptonic sector may be very, very important for those, for our universe. So I think the time is running out. So please let me, I did some exercise. Probably this is known to almost everybody, but I thought that the model with the right-hand neutrino, three right-hand neutrino with three active neutrinos is interesting. So I wanted to understand physics of this very well. Okay. So what I did was very simple. I just calculate the eigenvalues of this matrix because I wanted to study CP violation here. So this is a complex 6x6 matrix. And because of this, I calculated m dagger m eigenvalues, and we immediately obtained this. And I requested that first three should be approximately 0, and then the latter three should be heavy, right? And I just studied the constraint on this, and then I immediately find that I have a unique solution. And this is the unique solutions. And it's very interesting that ABCM and this piece is so-called inverse seesaw model. In the 0 lepton number violation limit, this is just the Dirac neutrino. Okay, and then this is kind of decoupled. And I thought that, oh, maybe if we think about collider physics where we produce right-hand neutrino at LHC or near future collider, this ABC is very important because A over M is essentially the mixing, right? Okay, between UE and heavy things. Okay, so I thought that this may be a good thing, and I tried. And actually, I tried many things. I tried to modify this completely, but then somehow I could produce just only one Majorana neutrino among our three neutrinos. And I couldn't find the reason, but then my friend Toshifumi Yamada told me that, oh, it's clear because maybe he also did it, he said to me that it's clear because there is only one ABC vector which links our flavor with a complicated, Majorana sector. Okay, because it's only one vector is connecting. No matter what I did here, the mass matrix which I can generate here is always rank 1. so I think he told me a few years or several years ago, and it was so discouraging for me, so I stopped. But maybe I can still continue. Okay, maybe this this part is too strong an assumption. We may need to break it a little bit in order to be consistent phenomenology with three right-hand neutrinos. But of course, by making the right-hand neutrino number to 4, it's very easy because double inverse seesaw can make 2 masses without problem. But as I told you, I'm quite prejudiced that if 15 quark-gluon leptons triplets, 3 generations, and if only right-hand neutrino is 4, that's so ugly that I don't feel like I even think about it. So that's my present stage. So my way of thinking is not kind of stuck. That's all. Thank you very much.
Okay. Any question? Yeah. If you have a question, he will deliver this mic to you. So yeah, Chung-Ang.
Thank you very much for the nice talk. I wonder if you have good answer to proton decay in the presentation. In general, if you have quantum communication theory, SU5, and proton decay is almost indispensable, cannot avoid it.
Yes, I believe that proton will decay, but I don't know when. That's the reason is actually we really don't know how that gauge symmetry is broken. We have many ideas, but the most fundamental thing is that we should split the 5-plet in SU5 into triplets and doublets, because doublets should be light, Higgs and Higgsino should be light, but the triplets should be really heavy. And this mechanism, there are many ideas, but none of them are really appealing to me. Maybe extra dimension type idea is probably most attractive, but still, I think we don't really know. So without knowing this, no predictions.
So you believe the structure itself should be there, but the actual realization may be possible some way.
There is no reason that proton can survive.
Thank you very much.
So if you take this scenario 2, if I introduce this what is it, dimension 5 operator, can you explain?
So scenario 2 is?
You introduced this dimension 5 operator.
Dimension 5 operator, yes.
And can you explain with that operator is all this experimental data?
Definitely, yes.
Definitely?
Yes. There's absolutely no experimental observation which goes beyond this operator. In order to find this, let me see. I think we definitely need a proof that the 3x3 mixing matrix is not unitary. Okay.
Yeah.
Then that violates. Okay. Then of course, if we produce right neutrinos. Yeah.
And then,
but neutrino that's beta decay, that's okay. It can produce it.
With that operator, you somehow neglect the renormalizability of the theory, right? Renormalizability.
Yes,
but this is the higher dimension operator.
But
and then this is also lepton number variety.
Yeah. I know that when I was a student, my teachers told us that when we construct a quantum field theory model, renormalizability is a kind of leading, principle. But during 80s, early 80s, when Weinberg asked us about the gauge hierarchy program, and Susskind proposed the Technicolor and those things. During those days, our idea of the role of renormalizability completely changed. I completely changed my basic standing point that renormalizability is just a consequence of some hierarchy which is protected by some symmetry. Okay, and there's no reason that non-renormalizable operator should appear, as long as this operator respects the symmetry for the dimension 4 piece. Okay, so this operator is completely gauge symmetric for under SU3, SU2, U1. Okay, and because of this, if this operator exists, then its effect due to electroweak and QCD corrections are really unstable. So it's protected. Okay, this type of operator, there's no reason to evade. Okay, and actually, this picture is now accepted by almost everybody in doing collider physics, and so all LHC physics and collider physics are now being done with the EFT framework.
Maybe this question is very simple. So this hierarchy is not almost to be decided by experiment. Do you have any theoretical ground, inverted ordering, or is it preferable, or normal ordering preferable? Do you have any theoretical?
I told you that I was shocked together with everybody else when the mixing angle turned out to be huge, right? It is because just like everybody else, I assumed that these mixing should be small in order for our understanding of generations. It was completely broken, right? Now, I use our knowledge about quarks and charged leptons that, this hierarchy is associated with the also mixing. Then, of course, normal hierarchy is more similar, okay, compared to inverted hierarchy. But I think that's complete prejudice. Until we know why, probably. So the point is, it may be worth spending your time or my time significantly to show that maybe inverted hierarchy is really true. Then the chance that neutrino-less double beta decay can be observed in the near future is higher. So you can wait for that. Sorry, it's not a very honest answer. I'm sorry. Yeah, I really don't know. Yeah.
I think we have sufficient time because